So we will be having hopefully our last session of the theory today. We'll be completing the syllabus. Uh, Before we start, I just wanted to share a few clips regarding what we covered yesterday. So here's the first one, and it's about the Earth's rotation and the moon and the sun. So this is a science project, obviously. And so what you can notice in this is that the Earth is rotating on its axis. So you'd see the globe spinning on its own. And then the Earth is orbiting the sun, and the moon is orbiting the Earth. So there are at least three different kinds of movements happening with the. And another thing that isn't highlighted is the fact that the moon also revolves around its own axis, and we're always facing the same side of the moon. Right, so just once more. Okay. Now, here's another. This is explaining why we have the reasons of the seasons. This is a TED Ed video.
Like Sun is the only planet that doesn't revolve around anything.
Hmm? Come again?
Yeah.
What did you say? I couldn't catch that. What does the sun do?
Like the sun doesn't revolve around anything.
So I mean, to give you a proper answer, the sun revolves around the center of the Milky Way. So the sun is also in motion, and so I'll share a video about that as well, which is really interesting. And the sun also has an axis just like the Earth, and it spins on its own axis. So the sun is not stationary, it's not just sitting there. Okay, so here's the TED Ed video.
When I was a kid, my understanding of the seasons was that December and January were cold and covered with snow. April and May were bursting with flowers. July and August were hot and sunshiny. And September and October were a kaleidoscope of colorful leaves. It was just the way the world worked, and it was magical. If you had told me back then that 1/3 of Earth's population had never seen snow, or that July 4th was most definitely not a beach day, I would have thought you were crazy. But in reality, seasonal change with 4 distinct seasons only happens in 2 regions on the planet, and even in those 2, the seasons are reversed. But why? A lot of people have heard of an astronomer called Johannes Kepler and how he proved that the planetary orbits are elliptical and that the sun is not at the center of the orbit. It was a big deal when he figured this out several hundred years ago. His discovery solved a lot of mathematical problems that astronomers were having with planetary orbit measurements. While it's true that our orbit's not perfectly circular, those pictures in our science books, on TV, and in the movies give an exaggerated impression of how elongated our orbit is.
By the way, if you notice in this animation, the Earth is tilted and they show an arrow, right? So that's the axis and the tilt. And it is also revolving on its axis while it is orbiting the sun. So
In fact, Earth's orbit is very nearly a perfect circle. However, because Earth's orbit is technically an ellipse, even though it doesn't look like one, and the sun isn't quite exactly at the center, it means that our distance from the sun does change through the year. Aha! So winter happens when the Earth is further away from the sun. Well, no, not so fast. The Earth is actually closer to the sun in January than we are in July, by 5 million kilometers. January is smack dab in the middle of the coldest season of the year for those of us up north. Still not convinced? How about this? Summer and winter occur simultaneously on the surface of our planet. When it's winter in Connecticut, it's summer in New Zealand. So if it's not the distance from the sun, what else could it be? Well, we need to also know that the Earth doesn't sit straight up. It actually tilts. And that axial tilt of the Earth is one of the main reasons for the seasons. The Earth spins on an axis that's tilted 23.5 degrees from vertical. At the same time, the Earth revolves around the sun with the axis always pointing in the same direction in space. Together with the tilt, the spinning and revolving causes the number of hours of daylight in a region to change as the year goes by, with more hours in summer and fewer in winter. So, when the sun is shining on the Earth, it warms up. After the sun sets, it has time to cool down. So in the summer, any location that's about 40 degrees north of the equator, like Hartford, Connecticut, will get 15 hours of daylight each day and 9 hours of darkness. It warms up for longer than it cools. This happens day after day, so there's an overall warming effect. Remember this fact for later. In the winter, the opposite happens. There are many more hours of cooling time than warming time, and day after day, this results in a cooling effect. The interesting thing is, as you move north, the number of daylight hours in summer increases. So Juneau, Alaska would get about 19 hours of daylight on the same summer day that Tallahassee, Florida gets about 14. In fact, in the summertime at the North Pole, the sun never sets. Okay then, it's all about daylight hours. I've got it. Well, no. There's another important piece to this puzzle. If daylight hours were the only thing that determined average temperature, wouldn't the North Pole be the hottest place on Earth in northern summer? Because it receives 24 hours of daylight in the months surrounding the summer solstice. But it's the North Pole. There's still icebergs in the water and snow on the ground. So what's going on? The Earth is a sphere, and so the amount of solar energy an area receives changes based on how high the sun is in the sky, which, as you know, changes during the day between sunrise and sunset. But the maximum height also changes during the year, with the greatest solar height during the summer months and highest of all at noon on the summer solstice, which is June 21st in the northern hemisphere and December 21st in the southern hemisphere. This is because as the Earth revolves, the northern hemisphere ends up tilted away from the sun in the winter and toward the sun in summer, which puts the sun more directly overhead for longer amounts of time. Remember those increased summertime daylight hours? And solar energy per square kilometer increases as the sun gets higher in the sky. So, when the sun's at an angle, the amount of energy delivered to each square of the sunlit area is less. Therefore, even though the North Pole is getting 24 hours of daylight to warm up, the sunlight it receives is very spread out and delivers less energy than a place further south, where the sun is higher in the sky because it's more tilted toward the sun. Besides, the North Pole has a lot to make up for. It was cooling down without any sunlight at all for 6 months straight. So, as the seasons change, wherever you are, you can now appreciate not just the beauty of each new season, but the astronomical complexity that brings them to you.
Now, obviously, a number of things that are mentioned were beyond the syllabus, but that gives you like a revision and a bit of more insight into the Earth's rotation and seasons and all of those things.
Like, I have a question.
Yes.
But then, like, why do areas like Antarctica never get any sunlight?
I'm sorry, the only thing I could understand was Antarctica.
Like, why is there no summer in Antarctica?
Who said there's no summer?
Like, there's always ice.
No, it's that during summer there's 24 hours of. Yeah, wait, Antarctica is which one? Is it in the one in the North Pole or the South Pole?
It's in the north.
Yeah. So, no, it's the southernmost. It's in the South Pole. Yeah. So it's in the southern hemisphere. So when there's summer in the North Pole, in Antarctica there'd be winter. So it would be probably night. Okay. Uh, we did that and that. Right. So here's a representation of how the solar system actually moves. Okay. So the thing is, as I mentioned, the sun is not stationary. Again, this level of detail isn't given in your book, right? But the sun is moving, and it's as you asked me. So the sun is revolving around its own axis, and it's also moving around the center of the Milky Way, right? So the sun is moving, and the planets, while moving with the sun, are like also moving to like with this, while moving around the sun, they're moving with the sun as the sun rotates around the center of the Milky Way, which is the name of the galaxy we live in. Right, so this is what the movement of the planets and the sun actually looks like. So it's not like the models that we make, right? Everything's like stationary. Here's another one. I don't know why they add such dramatically loud sound effects. So yeah, what they teach us in school versus what it really is like. What the teachers in school is something that I guess they're going to animate here. So yeah, quite different. I mean, you do get to know this, but much later on, right? That is if you pursue physics and astrophysics and stuff.
But like pictures of telescope, the Earth and all are like the same position.
The pictures of the planets and the Earth are the what?
Like in telescope, in pictures of like telescope and all.
Hmm. What about it?
Like they aren't moving or anything like
Well,
that.
obviously, like a picture by definition is like a
Like,
stationary shot. So obviously,
but like the background is always same.
that's because what we covered yesterday is because everything is so far away, right? And besides, I mean, if a star moved here and there, and like the whole galaxy and the universe expanding, so everything's moving. So maybe relatively, it appears to be in the same place, and plus the light that we capture in through telescopes or whatever are from stars that are so far away that possibly in the lifetime of multiple generations we won't be able to notice any change, right? So we covered the concept of light yesterday, you weren't there. And so uh, right, they are very far away, very far away, right? So by the time the light reaches us, it takes so much time that we get sort of a very old uh, image of what's going on. As if you review yesterday's lecture, you'll get up to speed with that. Okay, now with this, let's move towards the text and uh, to fulfill my claim. Uh, let's read through this and uh, right, plant a flag saying complete for the syllabus. So we are starting with talking about stars and their life cycle, and this is so like it might seem confusing a bit, but I just say just take it. We can go into details about it, but those kind of details aren't really required. So what you need to know is okay, fine, stuff like this happens, and that's how it happens the way they're telling us. So how do stars originate? So when interstellar clouds of dust and gas containing hydrogen collapse under the force of gravitational attraction, something called a protostar is formed. As the mass of the protostar increases, its core temperature rises. Gravitational potential energy is transferred to kinetic energy as the protostar contracts under internal gravitational forces. When the core is hot enough, so the temperature was rising as its mass was increasing. So when the temperature is hot enough, nuclear fusion can start. And so hydrogen atoms are joined together to form helium, and a star is born. If the young star has a very large mass, it forms a blue or white star. Right, so we talked yesterday about how the color of the star is related to its mass and its surface temperature. Right, so the more the mass, the more the surface temperature, the color will be blue or white, white being the hottest. And if the mass is less, comparatively the surface temperature is less, and so you'd get something that's either yellow or red. And so if it has a smaller mass and our sun is a star, so it's a yellow star, right? Or you could have something like a red dwarf that is more common. Okay, now the life cycle of stars. In a stable star, so one that in which the nuclear reactions are going on and will be going on for quite some time, right? Such as our sun, the very strong forces of gravity pulling it inwards are balanced by the opposing forces trying to make it expand to its extremely. So it's hot in the core, right? And so we know that when something's hot, it expands. So the core is trying to expand, but there's a lot of gravity pulling it inwards, and so that balances out, and so the sun is stable in that regard. This thermal pressure, right, the heating, arises from kinetic energy of the nuclei in the core, right? So the hydrogens and the nuclear fusion happen.
Can
When
we
the
make stars on sun on Earth?
hmm?
Can we make stars on Earth?
No, we cannot.
Okay.
Right? If I just go back, I believe they gave the temperature. Was it here or the previous section? Locating that particular piece. Ah, oh yeah, here it is. So, right, for the hotter blue or white stars, the surface, so the temperature of the surface, which is, right, obviously not as hot as the core, is 6,000 to 25,000 degrees centigrade. Right, that is the surface temperature of the, and for the sun, like the yellow and red ones, the surface temperature is 3,000 to 6,000 degrees centigrade. So yeah, no, not happening. Like there is an attempt to, you know, do nuclear fusion and stuff, right? But again, it needs very high temperatures. So if I just look it up quickly. Right, so it says that in 2022, very controlled nuclear fusion was achieved in a facility in the US, right? But as like very controlled, so not something that uh, would be similar to what's going on in the sun. And So the temperature of the sun and even higher have been achieved apparently within controlled laboratory settings, right? In China, for example, but again, very controlled settings. So they've gone up to apparently 5,500 degrees. And in some places, they've gone over 100 million degrees centigrade, which is hotter than the sun's core. So very controlled experiments. Now, to answer your question, so it hasn't been done apparently yet, but scientists are trying to create artificial suns on the Earth using nuclear fusion technology, right? And again, the experiments have, temperatures going up to 100 million degrees centigrade.
And like, what if a planet goes more near than the sun than usual?
It will collapse, it will burn up, right? So the solar system is actually very, very fine tuned. It's very, very fine tuned. Okay, coming back here. So yes, the thermal pressure arises from the kinetic energy of the nuclei and the core. When the forces are balanced, the star is in a stable state, which may last for up to 10,000 million years, which is basically 10 billion years. Right? So that's a nice long time, during which time most of the hydrogen is converted into helium. When the star starts to run out of hydrogen, right, so that's the point where things start going south. When the star starts to run out of hydrogen as a fuel for nuclear reactions, it becomes unstable. There is less energy being produced by nuclear fusion to sustain the outward thermal pressure, and the core collapses inward under gravity. So the balance between the expansion and the gravity is no longer there, and so gravity takes over and it collapses under gravity. Potential energy is transferred to kinetic energy so that the core becomes even hotter. There is a fast burn up of the remaining hydrogen, right, envelope, in contrast to the core. So the hydrogen on the outside is being utilized faster than in the core, and a huge expansion and subsequent cooling of the surface gases occurs. Right, so it expands and then it cools. And when it cools, it becomes red and turns into a red giant, or if it was much larger in size, it turns into a red supergiant. Then, as the core heats up, its temperature becomes high enough for nuclear fusion of helium into carbon, right? So there's a different kind of nuclear fusion going on. First, it was hydrogen to helium. Now it's helium fusing to make carbon. This will happen to our sun, in about 5,000 million years or 5 billion years, basically. Right? So there's still time. The inner planet Mercury will then be engulfed, right? So if then the sun expands, Mercury will be, taken up by the sun, and life on Earth will be destroyed because, yes, right, it's going to get much hotter, and life will not be able to sustain. So, right, then other stuff happens. So we've read up to this point that a stable star becomes a red giant. Then, depending on the mass of the star, it will either take one or the other. So low mass stars go go this route, where they turn into a planetary nebula and then a white dwarf and then a black dwarf, and this is what will happen to our sun. Whereas stars with much higher masses turn into supernovas, and then either into neutron stars or black holes. So let's quickly read through that. So low mass stars. For stars with a mass of up to 8 times that of our sun included, obviously. So what's the mass of our sun? Right, it is 1.989 into 10 to the power 30 kilograms. Right, it is about 333,000 times the mass of the Earth. And if we take a look at this particular image, yeah, this is an interesting one. Let me show it to you. Right, when you talk on mass, so that's the sun, and that's Jupiter, which is a giant, and you can see how small it is. So we remember I said yesterday a ping pong ball compared to a basketball, right? Perhaps even smaller, maybe like a bead compared to it, right? And the Earth is here. That speck you see, that is the Earth as compared to the sun. So that's how big the sun is as compared to the Earth. Right, and then you've got Mercury over here, apparently that faint thing you see. At the very edge there's Pluto, which is barely visible. And again,
Yeah.
Pluto isn't even considered a planet anymore, so so yeah, it's pretty big. And that's like a low mass star, just so you like what we're talking about, right? And that and up to 8 times that of our sun is considered a low mass star. So you can, I don't know if you can imagine the proportions that we're talking about over here. Right?
I
So
think there are other planets as well
sorry,
apart from these.
could you repeat that slowly?
Yeah. There are other planets as well, na, apart from these eight.
There are other celestial bodies, yes, there are other stars, possibly solar systems with those stars and the moons and everything. Yes. Okay. So when all the helium is used up, the core of the red giant collapses under its own gravity. Right? So it sort of implodes, it falls up inwards, and enough energy is released to cause the outer layer to be expelled. So it loses its outer layer. The small core becomes a white dwarf at the center of a glowing shell of ionized gas known as a planetary nebula. Right, so this guy over here in the image is that at the center that you see, that white dot at the center is a white dwarf, and all of this stuff, this is ionized gas and elements and stuff, right, as a planetary nebula. So if you guys have seen the original Lion King, like the animation, and that scene where Simba meets Timon and Pumbaa, and they're looking up at the skies. Let me see if I can pull that up. Just give me a sec. I found it. Let me share it with you.
Whoa, nice one, Simba.
Thanks. Man, I'm stuffed.
Me too. I ate like a pig.
Pumbaa, you are a pig.
Oh, right. Timon,
Yeah?
ever wonder what those sparkly dots are up there?
Pumbaa. I don't wonder. I know.
Oh, what are they?
They're fireflies. Fireflies that got stuck up in that big bluish black thing.
Oh, gee. I always thought they were balls of gas burning billions of miles away.
Pumbaa, with you, everything's gas.
Simba, what do you think?
So Pumbaa was right. Have you guys seen The Lion King, by the way?
No.
Oh, I'd recommend it. Okay, so right, our red giant turns into a planetary nebula with a white dwarf at the center. And planetary nebulae are thought to play an important role in distributing elements formed in the star into interstellar medium. So that's the ionized stuff out there. They have been photographed from the Hubble Space Telescope, but have a short lifetime of only 10,000 years, right? So yeah, that's very short. I mean, multiple human generations won't be around, but sure. Obviously, these are being called short in relation to the age of the universe and the scale at which things happen, right? So yeah, and these guys appear to mark the transition of the red giant into a white dwarf. So from a red giant, it turns into a planetary nebula with a white dwarf at the center, and then finally the nebula disappears and turns into a simple white dwarf, and that has a lifetime about a billion years and eventually cools into a cold black dwarf consisting mainly of carbon. That's what's going to happen to our sun in about 5 billion years. So, yeah, we have some time. Then we have high mass stars, stars with a mass of greater than 8 times, so 9 times plus, let's say, than our own sun. And we've seen how big the sun is, we know the mass, right? They are hotter than the sun and use up their hydrogen more quickly. Their stable stage is shorter and may last for only about 100 million years. Only. The core then collapses into a red supergiant. So red giant, if it's bigger, it's a red supergiant. And nuclear fusion of helium into carbon occurs, similar to what we saw with the low mass stars. When all the helium has been used up, the core collapses under gravity, similar thing happening, and it becomes hot enough for the nuclear fusion of carbon into oxygen, nitrogen, and finally iron. So this is new, right? The low mass stars only went up to carbon. This guy is continuing, it goes from hydrogen to helium, helium to carbon, then carbon to oxygen, nitrogen, and finally to iron. Right? Nuclear fusion then stops and the energy of the star is released into a supernova explosion. In the explosion, there is a huge increase in the star's brightness and the temperature becomes high enough for the fusion of nuclei into many elements heavier than iron to occur. So, right, in that explosion, the temperature gets so high that you get iron, you already have iron, you get other elements that are heavier than iron. Materials, including these heavy elements, right, they are thrown into space as the nebula, right? So that area of ionized gas and all that stuff. And then this material becomes available for the formation of new stars, and we saw how new stars form. Right, so just going back to that part, right? Interstellar clouds of dust and gas containing hydrogen collapse and all of that. So that can happen again. So they're available for the formation of new stars and their associated planetary systems, right? So other heavier materials come together and condense and form planets. The gases form stars. The Crab Nebula, something that was pictured using the Hubble Space Telescope. Here's an image. Is the remains of the supernova seen by Chinese astronomers on Earth way back in 1054, right? So in the 11th century. So about 1,000 years ago, right? It is visible through a telescope as a hazy glow in the constellation Taurus. And here's an image. The center of the supernova collapses to a very dense neutron star, which spins rapidly and acts as a pulsar, sending out pulses of radio waves. Okay, sure, that happens. If the red giant is very massive, the remnant at the center of the supernova has such a large density that its gravitational field stops anything escaping from its surface, even light. And this is what you get at a black hole. So just to look at that illustration again, in this case, red supergiant turning into a supernova, either going to form a neutron star or a black hole. So not both, but either one. So we read about the neutron star thing, right? So here's the black hole. In a black hole, matter is packed so densely, it is so like there's so much mass per unit volume, right? So a very high mass in a very less volume, that the mass of the earth would only occupy the volume of 1 cubic centimeter. So yeah, I mean, you can imagine the entire earth in between your finger, like your thumb and your finger, like 1 cubic centimeter. And of course, it's going to be heavy. So the entire mass of the earth. So since neither matter nor radiation can escape from a black hole, we cannot see it directly. Right? They mentioned radiation because light is electromagnetic radiation. However, if nearby material such as gas from a neighboring star falls towards the black hole, intense X-ray radiation may be emitted, which alerts us to its presence. Objects believed to be massive black holes have been identified at the center of many spiral galaxies. Okay.
Yeah.
So here's the last bit, the universe. Let's do this. So the Milky Way is one of the millions of galaxies that make up the universe, right? So, right, and galaxies are huge. They've got like millions, billions of stars and everything. So yeah, the universe is big. The diameter of the Milky Way galaxy is around 100,000 light years. 100,000 light years. So yeah, you right. So you can sort of put that into perspective how much that is, right? Remember, light years is a measure of distance, not of time.
Yeah. Yeah.
And it contains 800 billions or more stars. So just the Milky Way has 800 billion or more stars, and that's just one galaxy, right? And even galaxies are of different sizes.
Yeah.
So there are millions of galaxies in the universe. And so, I mean, I don't know what number to put up with the stars if there are 800 billion of them just in our galaxy. Now, the universe is expanding. So, in developing a theory about the origin of the universe, two discoveries about galaxies have to be taken into account. The first is that the light emitted from glowing hydrogen in stars in distant galaxies is shifted to the red end of the spectrum in comparison with the value on Earth. Now, right, it's something called the red shift. So basically what's happening over here is if there are waves, right, look the illustration on the left that says the Doppler effect. If there are two stationary objects. One is the source and the other is the observer, and they're waves. Like you flash a light perhaps, and they're waves, and so they'll cover that distance and the observer will see. Now if you are producing light while the observer is at rest, so they're not moving, but the source is coming closer, right? And so what you're doing is, what happens is that even though the waves are traveling, because you are moving with the waves, right, that light source, and so what happens, you can see in this illustration, the frequency and the wavelength seems to be smaller than what it actually is. They seem to be sort of compressed together, and so with a smaller frequency it appears bluish, right? So if the light, if the source is approaching the observer while emitting that radiation, right, it is they observe like a bluish shift, and that is called the blue shift. So they haven't mentioned blue shift over here, but I'm telling you, right?
Okay.
if
Yeah.
if the source is receding, meaning it's going further away, and so what you're doing is that while the light is, or the radiation being emitted, you're moving far away, and so the wavelength seems to be longer. It isn't longer, but it seems to be longer, and so the frequency is less, right? And so it appears reddish, it moves, right, and that is called the red shift. So, right, the light emitted from glowing hydrogen stars in distant galaxies, and why are they appearing red, right? That tells us the whole point, that the universe is expanding, right? Everything is moving away, the distance is becoming larger and larger. So, right, that's what's happening. So these observations can be explained if our galaxies are moving away from us very rapidly, not slowly, right? So it needs to be done fast, and further away they, and the further away they are, the faster is their speed of, so the further they're moving, the faster they're getting at moving further away. And so this tells us that the universe is expanding, and its rate of expansion is also increasing with time. So the more it's expanding, the faster it's getting in its expansion. So this interpretation is based on the Doppler effect, which occurs when a source of waves is moving. The source is moving. If the source approaches us, waves are crowded into a smaller space, and their wavelength seems smaller and their frequency greater. If the source moves away, the wavelength seems larger. Receding stars and galaxies are therefore shifted to the red end of the spectrum, right? Where the wavelength is larger, the frequency is less. Receding again means moving away. And they haven't talked about blue shift because that's not what's happening in the universe. The Doppler effect occurs with sound waves and explains the rise and fall of pitch of a siren as the vehicle approaches. So if you've experienced that, a police car, an ambulance, or a fire brigade or something, right, when it's approaching you and when it's moving away from you, the sound that you hear is becoming, it differs. And so it's not just with radiation, it's with sound waves as well, right? So when it's producing that sound is traveling towards you, but the car is also moving towards you, and so that is the blue shift, right? And so it sounds louder as it's approaching you. When it starts moving away, the sound is traveling to you, but the car is moving further away, and so that's the red shift, and so it sounds less loud comparatively. Okay, so the pitch rises as it's moving closer, it falls as it moves further away. The same effect is shown by light. When the light source is receding, the wavelengths seem longer. That is, light appears somewhat reddish or redder depending on the intensity and the speed and everything. From the size of the redshift, so how much red do we see? From the size of the redshift of stars, like starlight, the speed of recession of the galaxy can be calculated. So how fast is it moving away? The most distant ones visible are receding with speeds up to 1/3 of the speed of light. Up to 1/3. That means the speed of light is 3 into 10 to the power 8. That means it's moving by 1 into 10 to the power 8, which is 100 million meters per second. That is how fast the most distant stars are moving away from us.
Okay.
The redshift in the light from distant galaxies provides evidence that the universe is expanding and gives support to the Big Bang theory of the formation of the universe. Okay, what's the Big Bang theory? If the galaxies are receding, by the way, right, Haram, are you following? All right, Sobia said okay, so I'll take that as she's following.
Yeah. And I didn't say anything.
You said okay.
Yeah. I did before, not now.
Ah, so are you following?
Yeah.
Okay, so if the galaxies are receding from each other, meaning they're moving away from each other, it follows if you sort of work it backwards, if they're moving away, that means at some point they were all very close together, right? It is therefore possible that initially all the matter in the universe was packed together in an extremely dense space, in an extremely dense state. So everything that we see that as moving apart might have all been clumped together in a very small space, right? And so that would have been extremely dense.
By everything, does that mean the stars and the
Everything,
planets and
the
everything?
universe, the whole universe was concentrated in one spot. Now,
Okay.
one spot does not mean a dot on a paper. It means like in a very, as it says over here in the text, in a very dense state. So, right, in a small volume, relatively small volume, right? The whole universe. So, the Big Bang Theory proposes that this was the case and that the universe started about 14 billion years ago from one place with a huge explosion, right? So there was an explosion in that mass, that densely packed mass, and because of the force of that explosion, right, things started moving apart, and they're still moving apart, right? So distances are increasing. So the resulting expansion of the universe continues today, but predictions vary about what will happen in the future. So the critical factor appears to be the density of matter in the universe, like how much matter is there in the universe, right? If it's expanding, that means the volume is increasing, the matter is not changing, and so, right, the density will decrease when you increase the volume. That's mass per volume. If the mass is the same in the universe, the mass is not changing, volume is increasing, and so density will go down. So this is difficult to calculate because scientists currently believe that as much as 80% of the material in the universe is invisible. So there's a lot of mass that we don't even know is there, since it does not emit any sort of radiation, so it can't be detected. And again, this is like what scientists believe, so it isn't proven yet. It may be that this hidden mass exerts sufficient gravitational force to lead the universe to collapse. The gravitational force between masses not only determines the motion and evolution of planets, stars, and galaxies, but will also control the ultimate fate of the universe. Now, if it's any solace, most likely none of us will be around when that happens,
Yeah.
right? So maybe it's for, like, some distant generation of the human race, assuming the human race is around that for that long, right? For them to worry about. Okay, final stretch. Microwave background radiation, right? The class, I mean, I started earlier, so it's already about 50 minutes for the class, but I'll keep going, right? Because there's just this bit left. So
Yeah.
let's just
Okay.
do this. Okay. So microwave background radiation. The Big Bang produced radiation energy which still exists in the universe today. It's still there, it's all around us, right? And it exists in the form of what we have called cosmic microwave background radiation. So it's in the form of microwaves. Cosmic meaning it's in space, background meaning it's everywhere all around us, and radiation, obviously radiation of a specific frequency. So this was first identified in 1965 by these two guys as a background hiss in microwave signals picked up by large radio antennae. And so they went on and looked at it, and turns out that this background microwave radiation fills the whole universe with an intensity that is nearly the same in all directions. So it's everywhere, it's the same intensity, it's the same frequency. It was first mapped by NASA's Cosmic Background Explorer satellite launched in 1989. More detailed measurements have been obtained from the Wilkinson microwave anisotropy probe launched in 2001, and the European Space Agency's Planck telescope launched in 2010. And so this is an image over here of the cosmic background radiation as recorded by the Planck telescope, right? The red regions are obviously the hotter ones, right, with more intensity of microwave radiation. So this radiation left over from the Big Bang has maximum intensity at a wavelength of 1.1 millimeter. That means in 1.1 millimeter, one wave is being completed, right? So that's the wavelength. Yeah, they mentioned that. And it has been suggested that the slight variations in this value, hot and cold spots, may act as seeding sites for galaxy formation. And so that's the thing, right? Galaxies are still forming and possibly being lost as well, right? So, I mean, it's not like, something happened and that's the end of it, right? Creation and destruction is still going, right? Life in that is everywhere. So since the Big Bang, the universe has continued to expand, resulting in a red shift. So because it's expanding, what we notice is red shift, and that's why blue shift wasn't mentioned, right? In a red shift of the cosmic background radiation, so into the microwave region of the electromagnetic spectrum. So it's moving away, and so what we are observing is microwaves, which have a longer wavelength as compared to what it actually might be. The existence of cosmic background radiation provides strong evidence in support of the Big Bang theory and gives us an insight into the earliest days of the universe. Okay. Then we have the age of the universe. So this guy, Edwin Hubble, was an American astronomer working at Mount Wilson Observatory in California in the 1920s. And he discovered that the speed of recession of a galaxy is directly proportional to its distance away from the Earth. Right? So again, the further away something is from the Earth, the faster it is moving away from the Earth. We say the Earth because that is our point of reference. Right? So the further it is, the faster it is moving away. That's what this guy is saying.
But it still didn't exactly say that what's the age, like
What's the
how
age?
many.
Oh no,
Yeah.
we're getting there.
Oh, okay.
Right? And so this is called Hubble's law, and it can be written as v, which is the speed of the speed at which something is moving away, equals to h naught, which is Hubble's constant, and d is its distance from the Earth. Right? And so Hubble's constant can be calculated by the speed at which it is moving away over the distance that it is from the Earth. Right? Now the calculations are complex, but they tell you, they say all of this stuff. The Hubble constant represents the rate at which the universe is expanding. The value is found by measuring the speed of recession of a large number of galaxies whose distances are known. Redshifts are used to find the speed. of recession of a galaxy, and its distance can be calculated from the brightness measurements of supernova in the same galaxy. The maximum brightness of a particular type of supernova can be calculated and compared with measured values, and the apparent brightness decreases as the inverse square of our distance. Right, so if the distance doubles, the brightness goes down by 4, it quarters, right? It's an inverse square,
Yeah.
enabling enabling the distance of the galaxy determined, etc., etc. But then they tell you, after all of this, they tell you that the Hubble's constant is estimated to be 2.2 into 10 to the power minus 18 seconds. Sorry, per second. 2.2 into 10 to the power minus 18 per second. So what does that mean for us? So they give an example. This means that a galaxy 1 million light years away, how far is it moving away from us? So, right, V equals to h naught times d. So d is 1 million, so that's 1 into 10 to the power 6. So they skipped the 1. This is Hubble's constant. And so what you get is 2.2 into 10 to the power minus 12 light years per second. That is how fast it is moving away from us. So converting light years into actual figures, and so 1 light year is, as we did yesterday, 9.5 into 10 to the power 12 kilometers per second. And so you do the math and you get 21 kilometers per second. So a galaxy that is 1 million light years away from us is moving away from us at a speed of 21 kilometers per second. And that is fast. But then other stuff is moving faster because, right? If I just look that up, just give me a sec.
Yeah.
So,
Okay.
uh, right, the total size of the diameter of the observable universe. So this is what you're seeing over here. This thing, it is called the observable universe. That means that is the stuff that we can see. It is possible that there's stuff outside of this that we cannot detect. You know how big
Yeah.
that is, right? It seems like, oh, 1 million light years is a lot, but then
Yeah.
there's other stuff that is far away, and we already mentioned that it is moving at 1/3 the speed of light, which is, right, 1 into 10 to power 8, so 100 million meter per second. So 100 million meter per second would be how many kilometers per second?
How many was it again, you said?
Right, 100,000 kilometers per second. Right, so yes, and so that's because the observable universe is approximately 93 billion, with a B, right? 9 zeros, 93 billion light years in diameter.
Yeah.
That's
That's a
how
lot. That's a
big
lot.
it is. So the more distant a galaxy is from us, the faster it is receding, again receding, that it's moving away. Now they figured out, Hubble's saying that Hubble's law provides further evidence in support of the Big Bang theory. Okay. Now the age of the universe can be shown equal to 1 over Hubble's constant. Right? So you can see what they're doing, right? H was V over D, right? V equals to Hubble's constant times distance. And so H equals to V over D. And so if you do 1 over Hubble's constant, this flips and this becomes D over V. So that's what you have over here, right? So it can be calculated very roughly from the equation this, in terms of the distance and speed of recession of distant galaxies. We assume that the time for which two galaxies are close together when they are formed at the Big Bang is negligible, right? So when the Big Bang happened, they didn't stick around, they like immediately started moving away and very quickly. And the further away they're going, the speed is increasing. So, right? Uh, so the time together that the galaxy, the time in which two galaxies were close together at the start of the Big Bang, like at the Big Bang, was negligible compared with their present age. Right? If so, their age is approximately the age of the universe. So, assuming that these galaxies are as old as when the universe started, which equals to the time since the expansion began, because the expansion began immediately as the Big Bang happened. For two galaxies, assuming the speed of recession has not changed, that's an assumption, right? The age of the universe is the distance apart upon the speed of at which they're moving apart, right? And that is 1 over Hubble's constant. And if you do that, what you get is, right, 1 over 2.2 into 10 to the power minus 18, which gives you 4.5 into 10 to the power 17 seconds, because Hubble's constant is 2.2 into 10 to the power minus 18 per second, right? So this is how many seconds in terms of the age of the universe. So you convert that to years. So 1 year has 3.2 into 10 to the power 7 seconds. And so you divide the value we got by the value of the number of seconds in 1 year. You get 1.4 into 10 to the power 10. Otherwise, 14 billion years. And that is how, right, we have estimated the age of the universe, that the universe began 14 billion years ago, right? Now this is currently, maybe like a few thousand years down the line, if humanity is still around and they do these calculations, and so Hubble's constant perhaps would have changed, right? And so maybe they would get slightly, of course, I mean, the scale at which they're talking, that gone billions of years, maybe we won't detect much of a difference even in a few thousand years, right? But maybe there might be a slight change, and so, right, a slight different value for the age of the universe, maybe. And with that, I offer you congratulations, because we have reached the end of the chapter and the end of the unit and the end of the syllabus,
That's good.
right? So I had, that was a bit of a marathon at the end over here, but
Yeah.
hopefully you guys followed along.
Yeah.
Yeah, and right, so you can rest easy over the weekend. Inshallah, from next week we will be starting past paper practice. Now, obviously, with past paper practice, I would recommend that you revisit stuff. So for the IGCSE, they do have a study and revision guide, which is equally useful for the O level as well. The O level doesn't have a separate study and revision guide, so we can use the IGCSE one, right? Given whatever differences there are, but the majority of it is the same, so it's useful. And yeah,
Okay.
anything you guys like to say,
No,
Haram?
just thank you.
Oh, you're
No.
most welcome. Right. So yeah, have fun.
Okay.
Have fun
Okay.
until next time. And yeah, see you around.
Yeah, Allah Hafiz.
Allah.
Love.